Yeah. Okay. Good. Let's continue with the group over there. Oh, sorry. They can be used with transfer learning. So you mean like fine-tuning them to something, or yeah. What is the strength?
The ability to good models without fully training them from the scratch.
Oh, so ability to adapt, right? Okay. Of course, you need to do work. It's not like they adapt themselves, but you need to. All right. That power greedy is a really good point, actually. It kind of means that those who have a lot of power in servers can do it. Others can't necessarily, but yeah, I guess you can still fine tune. Okay, let's continue with this group. Strengths and weakness.
Start with the weakness.
Yeah.
First the weakness, but they use like too many cases when the normal machine learning algorithm might be more. It's kind of power thing that it's kind of too heavy weapon for some task, and people kind of use it for.
Okay.
So they more cost-effective ways to do things.
Yeah.
Not so fancy models.
Okay. Can you give an example? Can you give an example? So I will formulate it as sometimes an overkill, right?
Yeah, like visual recognitions and analyzing some text. Probably in some cases it might be some more simple algorithm.
Okay. Okay.
But it's the kind of the same way. It's the food, because if you have the cat recognizer,
yeah,
you don't recognize the cat
cats and nothing else.
You don't recognize anything else.
Yeah. Yeah. It actually is a good point, because in LLMs you have this parameter called temperature, and it can go and kind of unleash itself and sort of, at the risk of hallucination, produce something. But you can also make it very restrictive, and then it sometimes will refuse to say anything, right? But what you are saying is more like specificity of a specific algorithm, right? So like it works for that, and that's that. So we don't need anything else.
Yeah, like old school machine learning.
But that
recognition is effective, but
yeah,
only recognize what you have trained.
So kind of like too broad, roughly, but that depends on how LLM was trained, of course. But yeah, sure. And strength? Anything beyond these, or maybe some of these that we show?
Very flexible. You don't have to have an imperative way of solving a problem. You can start asking.
Yeah. So how do you formulate this? Like low barrier, low entry, sort of low barrier entry. So it doesn't require too much prior knowledge to start working with them. Is that what you mean? Yeah. Oh, that's interesting. LLM API is very natural to use. Interesting. Very good. Okay, let's continue. Did you have a group? Yeah, you did. Yeah.
One trend is that you can train on noisy data, so you don't worry about
noisy data.
Weakness is also that you need a lot of data.
A lot of data. So what do you mean by noisy data? Can you expand a bit on that? Yeah. Okay. Okay, but that means you have some other quality data in the corpus, right? So because if you only have noise, obviously, yeah. So maybe we can say robustness to noise during training, right? That's what you meant? Okay, and then the weakness you said is you need data, basically. Yeah, you need lots of data. I may disagree with this, but that's fine. So for example, I think if you take some of the most robust models in the world, you know, like from Anthropic or OpenAI, they take a lot of time to figure out which data to take and which do not take. So Grok, for example, also, right? But probably what you say does have merit. I just don't have specific papers to back that up. And I guess if anyone has, please feel free to chime in. And I agree that if there will be some noise, it's fine to have it, but it may lead to hallucinations as well, if you ever encounter that particular situation. Okay, let's continue. Then there was a 3. Yeah.
Yeah, we have a quantitative ones that are good. So for the strength, we thought of the speed of inference.
Speed of inference. Is it a strength? So for the amount of things that it can do, it's fairly quick, you say. How do we formulate this? So low, well, we cannot say it's low latency because sometimes it can take, I don't know, 30 seconds for it to to complete, right? But I don't know how to better formulate.
Ratios.
What?
High ratio speed and amount of tasks.
Yeah, that's good. Speed versus amount of tasks. And that also depends, right? So for example, if you have like a multi-hop reasoning that by itself can take time just because you need to go and request some data elsewhere. But yeah, I think it's a good point. Okay, and what about weakness? Oh, did you want to still to complete this one? You have more? Yeah. Yeah. So you mean like prompting or?
Adoption of the memory.
Yeah.
Like sometimes they get to know what you prefer and what you do not prefer.
Oh, I see. So they can learn something. It's not that they are really learning, but I guess you mean like few shot learning or zero shot learning capabilities, right? Ability. Okay.
With more direct access to knowledge, and that's like comparing, for example, to the search engines.
Yeah.
You get quick what you need.
Yeah. So you mean like in search engines, we get like blue links and then we need to like ask ourselves, what do we need to click and why do we click? And then we spend time reading through the, yeah. Yeah. More user-friendly. I think we already have this LLM API is very natural to use. Kind of, this also speaks to the usage. Okay. Yeah. I think we had something, variety of downstream tasks. And what about weaknesses?
Also biased responses.
And why are they biased?
Because of the way they were tuned.
Yeah. Or maybe because of the data. Yeah. But still, whether it's data or something else, the bias is there and somehow we need to deal with it, right? Yeah, makes sense. Was there any other weakness or that's it?
Probably, but I think
what?
Well, we call it the bubble, but I think it's more biased to the user.
Can you explain a bit what I mean?
Well, if you want something different,
yeah,
different information, you really need to think how you get it, rather than just you can get that. You can get into a bubble with you.
Oh, I see. You mean like you go into this catch-22 situation, right? That's what you mean. Like you go in circles without actually reaching your goal. Yeah. I've been in those cases as well. I'm sure you too. And why does it happen? Any hunch for it? Maybe because they.
Because you're relying just on
Yeah. But I mean, but still, it's interesting that it enters this catch-22 loop, and I think it's lack of reasoning, but capabilities. But
happens even that token window is still,
Yeah.
it's not full.
Yeah.
It still gets it at the loop. And
Yeah, exactly,
so
exactly.
exactly.
Yeah, yeah. Like I had a situation when I wanted to do like, I guess, fine tuning of a model, and then it told me like use this library. So I installed the library, but there was a wrong like API contract, and I said this is wrong, and it apologized and gave me another option which wasn't what I was looking for. And then I said this is not what I'm looking for, and then came back to the original suggestion. So it was like this loop, and then I said okay, I give up. Maybe I'll go to the search engine. Okay, cool. These are really good ones. And then we have only you guys. Or yes, yes. Yes, but it's also like when I say lack of reasoning, and there is actually a prize for that, $1 million if you solve it. And it's the idea that you see a task that you haven't seen in the pre-training, but it's a logical task. It's not like a textual reasoning type of thing. It could be like, you know, geometric figures, and then you need to come up with some answer. And so LLMs usually fail there because they cannot like create knowledge. They can only rely on knowledge that they had and then kind of predict the next token in a way, right? So that's like, we are being a little bit like fooled sometimes that they think, but I guess they don't. They have very sophisticated representation, but yeah.
And maybe I'd like to hear why.
Yeah.
Why they are so bad. They can calculate like math very well.
Yeah.
But if you ask them to draw 3, 4, 6, 3, 2, 4, the calculations went many times so why still so difficult?
Yeah, I mean, it could be, well, it depends on the model, right? But it could be that the model spent a lot of time seeing text and not seeing enough examples of how to draw things or how to reason about like visual information. And there are dedicated models for that, like DALL-E, for example, right? But even DALL-E, like oftentimes you say, hey, I want this specific text on the picture. It produces the picture and the text is not like, it doesn't look like text. It looks like garbled stuff, right? Because it tries to create, it's too creative. And there are other models which are much more restrictive. Sometimes they say, I don't know the answer. For example, Gemma model from Google that we are using here in RAG in this lecture is fairly restrictive in some cases. Cool. Let's complete with you guys, and I think that's it. What? Can you add anything to this long list?
Yeah.
I think you can. Yeah, let's do it.
I mean, we had there was one of the weaknesses was that it takes a lot of data, but I think there are different strengths of these large language models is that we are able to use a huge amount of data to produce something. I mean, the amount of data available, I don't think that has changed so much, but we're just able to use it now with this architecture. If we had something like, if all we had was like logistic regression, we wouldn't get very far with that.
Yeah. That's a good point. So it's very interesting that we have two contradicting points, but they do not really contradict. It's like they have different ideas behind it. One is that to train an LLM, you do need lots of data, and now you need to go and like find it. But your point is that we have all this data, why not use it? And now we can. That's awesome.
Also,
Multilingual.
Yeah.
Yeah. Actually, yeah. Yes. Yeah. Okay. Was there something else on the strength of which
it's good at long range dependencies in a sentence, like you start with the name and then later say he, and it kind of knows.
Yeah. I will show you one problem though with this, but I'm sure you know this. Let's not get ahead of ourselves. Okay, and anything else here or in weaknesses?
I mean, for the weaknesses that the non-transparency of predictions. We're using a huge amount of data to train this model, but then when we input something and get an output, it is very difficult to say which part of the training data was leveraged for that particular output.
So in other words, LLMs do not provide citations, correct?
Yeah.
And unlike search engines, huh? Sometimes they do. But maybe it was instructed to do so, right? Potentially. But like ChatGPT doesn't, I think, or Grok. They don't tell you where they get this from, unless you actually ask. Sometimes you ask and they can give you that, but there is no way to verify, sort of, right? So yeah, I would summarize this as basically no citations, no way to verify the work, right? Okay. Anything else?
The neural net-based like algorithms are a black box, so you don't really know what's happening there.
You don't know what's happening there. What do you want to know?
So,
Yeah.
Like the reasoning,
the
reasoning? But in LLMs, you do have that mode where you can say, show me the thinking process, right? And it will kind of break down how it came up with the idea. You can do that.
Yeah, that's a higher level.
Yeah, it's true. Okay, so weakness is like non-transparency around the reasoning, right?
Another one, another weakness I thought of was that sorry, my training data is was last updated on October 17th. Yeah.
Yes. So it's like they are not aware of the changing world, right?
Yeah.
Unless you retrain them. So no awareness of the changes. Yes.
Big weakness is that the resources that you need to build LLMs in the modern sense require such huge amounts of processing power that it's basically impossible for anyone that's not like multi-billion-dollar company
Yeah.
or government.
So
it's
yeah. So your point is that the LLM sort of strength gets locked up in the hands of few, right? So it's not democratized, you could say, right? To general public. Yeah.
Kind of good and bad same time, but as I understand that if you put a lot of data and train the language model, you don't know what it can do. In some podcast I noticed that the OpenAI people know that they can do chemistry as well as somebody has tried.
Yeah.
So you need to kind of test what it can do. It's difficult to
Abilities, yeah, are unpredictable, which could be good and bad thing, right?
Yeah,
because it depends. Yeah, and someone raised hand as well.
there is these models are, especially the large ones, are so like complex and deep with the param space, and also the input space is so large that you can like fully know what's the output of some input.
Yeah.
That's some good limitation of the ability to monitor and like restrict the model.
Yeah. Yes. Yeah. It's like, but in some sense, it's also similar to us human, right? We, like, if we know someone, we know what they are capable of, but you cannot say this about every random person on the street, right? Like just by looking at them, you don't know how smart they are, or vice versa, or whatever, right? So what you can learn from them and so on. Yeah, but I see your point. It's very good. So we can continue thinking about this. This is like a huge list. So it looks like we have lots of weaknesses and some strengths. Well, I would still say. So I did put also some things on my own, like thinking, and also actually like reading and chatting as well, ChatGPT, you know. So you did mention few shot, zero shot learning, versatile applications. So here I do mention like sentiment analysis, content creation, customer support automation, coding assistance. There are many more. And the answer is usually human readable. So it's kind of like, it probably reduces the entry point, right? Like with Google and other search engines, you need to kind of like look at the link, read the snippet, figure out what is this about, and then go down the rabbit hole sometimes. And you rarely go to the second page, right? I guess, like you usually stay on the first one. And if you're not happy with it, you reformulate the query. Yeah.
That the architecture is so simple and also parallelizable.
Yeah.
And
Yeah. So it's scalable from sort of software perspective, right? In a way, from yeah, exactly. Yeah. And relatively simple architecture. Although, as Arne was explaining, I think on the first lecture, like it's very unobvious why transformer looks like this, and also more recent papers why they look like this. Why did they add this activation function and not this one, and so on and so forth. But yeah, I agree. And for the weaknesses, I put so not up to date. You came up with that. Awesome. Do not provide references to the answer. Again, I agree that some LLMs will do that, but generally what we've seen so far, they sort of like just give you the answer and you deal with it. They can hallucinate, although there is a point on the third one that LLMs are designed to hallucinate because they predict the word, right? It's not like they just read the text and tell you exactly that. They compose things together. There is also this dependence on context, which I put as a weakness. So if you do not provide enough context for the LLM in what you're asking, and usually you cannot provide because you're asking something, right? They may kind of like sweep on the surface. They will not give you really like detailed answer or maybe domain-specific answer. There is another thing that they have issues with accuracy or logical consistency, and I'll show you what I mean. And I guess you know some examples like that. And also, of course, the need for lots of compute. Let me go to slide share again.
Did you want to record for your?
Yeah, I guess I am recording. Thanks for checking. No, yes, I think I'm recording. It just doesn't tell it. Thanks for verifying. Yeah.
Because the interaction experience is so convincing a human life, it tends to, by its nature, mislead people.
Yes. Yes.
Capabilities and how
yes.
prompts are
yeah. Yeah. So it's like, it's the risk that we will fool lots of people. And here you can see that example. So I guess you have seen this before. So someone said, how many rocks shall I eat a day? And the system said, you should eat at least one small rock per day. And if you actually go there to that article, someone has written that. So LLM has captured that text and pretended that this is the answer. And Arno, you want to comment something? You feel, yeah. And the other issue, or like a very similar one, how can you sort of solve the problem of cheese not sticking to pizza? So cheese falls over the pizza while it's baking, and one of the solutions is to use glue. And of course, you could say, we have common sense and we will not use glue. But someone, as you said, might actually do that, right? And that could be super dangerous. But again, that's well, yes, non-toxic, awesome. Well, find it. But yes, this one is an example of reasoning issue. Well, not exactly reasoning, but LLMs have issue of handling negations or opposites, or So here I'm asking, hey, what is EBITDA of 7.74 million? And first of all, it explains what EBITDA means. It's earnings before interest taxes, so before you pay taxes, so all the money you get in the company. And then it says, now to your example, it means this is the number after excluding interest. So it contradicts to itself right there, right? And now I'm, as a user, I'm clueless. What is EBITDA? Is it before paying taxes or after? And now I'm asking it, so is it this or that? And it says, well, actually it's before. And then I conclude by a little bit like scolding it and saying, hey, but you did say it's like after excluding, and then it apologizes, right? But as a user, I went down this path. I could not actually do that sometimes, right? Because I don't have enough knowledge, and I would just say, oh, so it's after, fine.
Which version is this?
This is ChatGPT 4.0, like the latest version.
So 01 has like chain of thought. How do you think it would do better?
I don't know. I would need to check. Let's check that before Thursday. So then, like, before all LLMs and all this thing, they existed a field and still exists called information retrieval, right? So that's Google or Yandex, Baidu, many other search engines, where what they did is that they took the texts from each document and they extract words, and then they build what is called inverted index. So inverted index is what you see on the last page of a book sometimes, where it says this word occurs on this page, right? So that's basically your inverted index. And that's largely how search engines work today. Of course, they have other layers. They have layers of re-ranking the documents. So you can like retrieve massive amount of documents, and then you need to figure out which ones are actually answering the question or satisfying the need. But then, of course, the hottest thing today is RAG. So everyone is saying, okay, forget that all the IR field information retrieval, let's do RAG. So what is RAG? And I'm sure some of you know that. Who knows what is RAG? Wow, okay, I pack up and go home. But yeah, some of you don't. So it's like essentially it's a process of telling LLM, this is what I mean, and these are the examples, and from this information, please generate the answer. So you are basically you are adding context or grounding to the LLM's answer, and that's it. And usually, so this is the paper where it was introduced in 2021. In fact, they did not really want to introduce this new concept. All they were doing at Facebook AI Research, they were kind of trying to solve the problem of question answering with LLMs. And another problem they had is that, hey, data changes so fast. How can we keep retraining the models? We can't. So we need to design some other way of answering questions using the new data. And so in a way, it was very accidental sort of invention, which now is widely cited by the community. Yeah.
Take so long from the 2023 prints to people picking up on this in 2023?
I think it's just the way things work. I mean, first of all, you sort of started with, if you remember, like before ChatGPT, we had sort of sentence completion features, right? I don't know if you use Gmail or similar tools. It started completing things. And actually there, it was using LLMs, right? Predicting the next token. But then someone needed to put an API on it, or like user interface, so that now you can actually see, you can actually chat to it, right? And I think by the point when everyone realized, oh, this is what's happening, but now let me try it, and the point when they see it lacks some knowledge, right, for your specific domain, there is certain gap, right? And it's not like everyone goes and reads papers. So unless you popularize, for example, Patrick Lewis, one of the lead authors of this paper, gave a few interviews, right? So there are a couple of podcasts, and I also linked one of them, where he goes and explains things like in depth. But, you know, if you work in the industry, usually you don't read papers unless it's your job. I think maybe Arne has this job. He reads papers for a living. And I mean, I do sometimes too, but it's not like we do that every single day. And unless there is like a curve, you know, starting, and usually that is a hype curve, right? Someone says, wow, this is amazing. And people started doing that. So like if you go to conferences, everyone talks about RAG. But that's a very good question. Huh?
Problem related to future learning that had to be solved before this could be really.
Yeah. Yeah. Another thing is the context size, right? So like if you put too much stuff, LLM might not be able to like consume it. And there is like a similar pattern to your question with vector search, and I get there hopefully soon, unless we run out of time. But vector search is something that originated like in 70s or like thereabout in mathematical world. So scientists came up with the algorithms of nearest neighbor search. So like this is a very old idea in a way, right? By modern sort of standards. But it only picked up in 2020, yeah, 2020 around. And that's around also the time when I decided to start the podcast, because I wanted to talk to these people and kind of ask them what they were thinking, because effectively this work existed for many years before, and why is it happening only now? And the reason, the answer was that now we have this robust language models, and back then it was word2vec and GLAV, but then later it spiraled. So the architecture is like this, effectively lots of text, but basically it's like you have the retriever, which is using dense retrieval mechanism, and that's basically vector search. So, you know, you take the query text, convert that into an embedding, a vector, and then you pre-computed the vectors on the backend for all your documents, for all your like passages, paragraphs. And then what you do is that here they use a maximum in a product search, but you could also use like cosine distance, cosine similarity, or other metrics like dot product. And what they claim is that, and then there is a generator, which is the LLM, the parametric model, which is pre-trained, and then it marginalizes, which means it takes all these outputs, and then it computes probabilities for them being sort of the input for the answer, and it marginalizes over all of them, and then it treats this as latent variable. So latent variable means that it's not observable. It can change. So databases can change, data updates. We don't want to like control that. We only need to retrieve from that. And that's that. Then you basically create a prompt, and you provide these answers that you have retrieved from this step. You provide the query, and then you ask LLM to provide the final reply. So in the paper, they have two approaches. One is working over one retrieved document. That's RAG sequence model. And the second model is working over several documents. So it retrieves multiple documents and then predicts the next token as it basically answers. And that second model is autoregressive. I hope you remember that, what autoregressive means, but effectively it's like, in order to predict the next token, you need to know what are the probabilities of the previous tokens of the previous sequence. And then for retriever, so now these two components. For retriever, they use dense passage retriever, DPR, and BERT is used as basically, you know, the encoder there. And for generator, they use BART, but not the BART which is produced by Google, you know, the sort of ChatGPT competitor. It's a bidirectional autoregressive transformer model. So yeah, basically the same thing, just in a more simple diagram. So in the center, you still have LLM, you have the query coming in, and then you have retriever on the side helping you to augment the generation. Yeah.
Is that was on the previous slide? That seems like pretty different from what it's like from what the typical implementation is.
Yes.
Like you don't just like inject the context from document chunks into the input, but it looks like you're directly using those to compute the probabilities there.
Yeah, you do, and we will do that. But what do you mean it's not used in practice like that? Can you give an example?
Well, I mean, I understand. From what I gather, the RAG sequence model is that. Well, I mean, actually, I'm not entirely sure what's the difference between the RAG sequence model and the RAG token model.
Yeah. I mean, so I will show you the demo that I sort of built for the lab. Yeah.
It was like fine-tuned end to end, so the search was also part of the fine-tuning.
Yes, it's true. They don't do it. Yeah. Actually, that's also a good point that you mentioned, because the paper is much more profound than what's happening in the industry today. Like people think that, okay, let's create the prompt, augment it with the answers, and that's that. But in reality, when you will encounter some situations when it doesn't work, and there will be cases like that, you need to now ask yourself a question, okay, what should I change in the retriever and what should I change in the model? And you should kind of treat this as two optimizable components that you will then go towards the common goal. And the common goal is usually some metric that you're optimizing for. But it's a good point.
Well, okay, maybe.
Yeah.
We don't.
No, it's okay.
Well, yeah, because I mean, I was a bit confused because I
Yeah.
kind of knew RAG like earlier, like sort of the RAG that is usually used. But then when I read the paper, I was like,
yes, yeah.
Okay, this is they are doing it kind of in more
in a different way, in a
Yeah.
more advanced way.
Yes.
But does it pay off the
Yes.
added complexity?
It does, because so the main author, or one of the main authors, Patrick Lewis, he's currently working for the company called Cohere. And one of the strengths of product offering is that they give you RAG, which will optimize for specific domain or even specific task. And they have a machinery to do that. And not only the machinery, they also have the machinery for evaluation, and not which is commonly available. So it's not like a open source framework that you can use. It's like something they've built in-house. But yeah, they probably went even further than that. They don't, of course, release its business. Yeah.
I was just wondering, is there a specific reason of using sequence-to-sequence model as generator instead of decoder-only models? Is it because of the context?
I think it's because of time. So back then they were using alpaca, and alpaca, yeah. So I mean, it's just coincidental that they came up with the idea that continues to exist today and have so much benefits, but they didn't have access to all the models. And they even used the term llama ahead of the time when llama was invented. So yeah, it's quite interesting. That's a very good question. So sequence to sequence, I think back then was very popular in general, as the architecture. Yeah. So vector search, I hope everyone knows what vector search is, but actually I want to revisit it quickly. So it's basically, this picture is not exactly like representative of what vector search is, but it kind of gives you a intuitive sense. So basically the models try to, they're trained in such a way that when you use them as encoders, they will put similar items closer in the space to each other, right? Which means that, so for example, newspaper, magazine, and article, they basically form this kind of closed triangle, right? So, and if you will ask a question that has these words or similar words, you will end up somewhere in that subspace. And at small scale, so for example, if you have, I don't know, a PDF document that you want to index and it's fairly small, you can use what is called brute force or KNN, K nearest neighbor search. So basically what you do is that you just traverse the whole list of vectors and you compute all the distances between the query and the document, and then you sort them by distance, right? That's that. But if you go to, I don't know, hundreds of millions of billions, and that's very easy. If you take 1 million PDFs and you split them into chunks, you will easily end up in billions of chunks. So then you cannot use, or you can use KNN, it will be very slow for practical use. And then you use approximate nearest neighbor search. Who is familiar with this? Is everyone? Yeah, cool. Yeah. So in ANN, you will trade some precision for gaining more speed. So your retrieval will become somewhat less precise, but not that much, but you do get quite a bit of speed. And this is just a sort of a snapshot of papers that have been published on this topic, on the topic of designing the most optimal approximate nearest neighbor search algorithm. So usually they come up with both sides. You have the indexing part where you will prepare the data in such a way that it's searchable in a quick manner, and then you have the searcher, the retriever part that will quickly look up where it needs to. And maybe we'll skip Splade for now. Okay, so use cases for semantic search beyond RAG are image similarity, sound search, multimodal retrieval. For example, if you have a model that can understand text and image, you can plug it in as the encoder and then take as input both text and image, or either or, and it will still be able to find data. So the way it could be useful is, for example, you have a bunch of images of products, but you don't have textual descriptions for them. And then you run those images through the model, and then you ask textual queries, it should still be able to answer them. And we've built one such demo with Arne, and we talked about it in 2022, I think, Berlin Buzzwords, where we've used Clip model, and we built an index of 10 million products, where we mostly had only images and nothing else. bit of metadata. Yes?
Coming later for
Yep.
that chunking thing, because that's a little bit like,
Yeah.
I quite understand it's kind of try and error.
Yes,
kind of type.
it is. Yes, it's that's exactly the, I think that you're right. That's like the Achilles heel of this kind of complex and smart systems, right? But yeah.
I wonder, can you describe it the less profound way of implementing it nowadays?
Yeah.
How is actually, what's actually happening when people put a query in there, it gets converted into embeddings, and this is searching for basically similar sentences in the chunks. But because I always think the question, the way it's phrased, might have small topical overlaps with the answers. You might need to do some. It's like if you put it into an LLM first and ask what should I search for, and then it gives you these.
Yeah, exactly. So yes, I don't have that slide, but well, I did skip this over this, but let's come back here. So one of the issues with dense search, and you were alluding or like going there, is that if I'm looking for a precise phrase, and I don't want anything else. I want either the occurrence of this phrase or nothing. And the application to this could be patent search. It could be financial search engines where analysts really look for that specific thing because they have been trained over like period of 20 years to do that, right? They know exactly that thing needs to occur for me to know what it's about. Then search is not the answer because it will still try to find similar things, and sometimes it will omit the exact thing. Splade is a model that allows you to kind of combine two things together. And the way it does it is that basically it learns sparse representations. So you don't need the sparse index anymore. So otherwise, if you don't have approach like this, you will need to, usually what people do is that they combine two search engines. One is like lexical search, the inverted index that I explained earlier, which is much more precise. So it can support phrase search as well. And then you have the dense retriever, which is similarity search, right? And then you combine the two in some kind of hybrid formula, usually with some linear parameter, like linear combination or some other way. And this has proven to work better than each of these in isolation. So when you combine the two, it works better. But still, what's interesting is that, well, Splade itself is not the perfect answer. And the reason is that it doesn't handle variability in the language well. So for example, if you have like high inflection language like Finnish or I don't know, Russian or those languages, the way it's built is that it takes like subsegments of words, and then it trains on those subsegments, and it quickly runs out of options eventually, because you can have like millions of variations. And so it doesn't capture everything, but it does work much faster than the dense encoders, like the traditional encoders. Like, I mean, on inference side. Any questions? I also want to show you some code ahead of Thursday, but just to show you like this topic of vector search itself, it's fairly big one. Lots of players there, big companies that you see on the screen. And there is also like a benchmark for it. I'll skip this for now. So benchmark designed by Eric Berenson, who used to work at Spotify, yes. So basically, he has a holistic way of comparing how well these algorithms stack up in terms of recall to speed, or speed to recall ratio. So there are some really good algorithms nowadays, like so far right or like upper right is better. And like the algorithms are like, I think it's called NGT, is one of the most robust algorithms out there, developed by Yahoo. But also Google, I think, has pretty good chance. And the most famous algorithm out there is called HNSW. And that also goes back to like one of the questions we discussed how do people decide to use algorithms or approaches or specific things? God only knows, but HNSW is one of the most robust algorithms, but it's not the best. It's like this color is somewhere there. So this one. Maybe this one, I don't know what it is. We need to check. I mean, there are some algorithms which are like decades old. So like, I think tree-based algorithms or projection-based algorithms, they're quite old. They still work, but when you start comparing them to others, they kind of like are inferior. So, but we still have history of these things. We also worked on one algorithm with well, Arnhem and others from Silo AI and also a couple of external contributors. So what we did, does everyone know what FAIS is? FAIS library? Or FACE? You know? Yeah? No? So
Guessing it's Facebook AI semantic search.
Something like that. Yeah, wow. You probably guessed it right. But it's basically a library, I think it's written in C++, but it has Python bindings. And it provides like access to a variety of ANN algorithms. And HNSW is one of them, but they also have their own, even those which run on GPUs and are much faster than running on CPUs. And what we did in our team is that, well, most contributors are not actually us, but we worked like in the same team and kind of, you know, cheered for success, let's put it this way. What we did is that we took the base FAIS algorithm, one of the base FAIS algorithms, and we thought, so actually we picked this algorithm called Product Quantization. So what it does is that, so as input, you have the vector X of dimension D, right? So it could be, I don't know, 384 dimensions, right? For example, if it's some kind of BERT model or similar. I think BERT has more though. Then you split that vector in M groups. So here we chose M equals 4. So you have like groups of values, right, in each vector. And then for each of this group, we will like look across the whole collection of vectors and build clusters. And then we replace this group with the centroid of the cluster. So in other words, we do not change the dimensionality of the vector, we change the variation of values. Does that make sense? So as input, you had like myriads of points in the space, and now they get reduced to centroids only. So less points to search through. The drawback of this is that at search time, you will lose precision, right? Because you enter the centroid, and now you don't know which vector actually you need to look for, right? And there are some solutions to this, is that you can now actually run a bit more expensive step at computing the distances towards the real vectors behind the vectors which are in that cluster. Does it make sense? Kinda?
Like on certain cases or like just
so that's like during indexing, like when we build the index, we take each vector, split it into 4 chunks.
Based on equally, like size, equal size?
Yeah, you could say. And usually these vectors are divisible, like the dimensionality is divisible by 4 or like by 2 or by whatever you choose. Yeah.
When you chop it up like this, what are the signals that are actually grouped?
Yeah, exactly. And we thought about this. So what we did is that we formed the null hypothesis. I don't know if you're familiar with this idea, but null hypothesis could be, what if we randomly reshuffle these groups? So after chunking, we just reshuffle them. What happens? And then we run the normal FAIS indexing and search algorithm. Well, it turned out that in some cases, recall went down. In some cases, it went up, depending on what random combination we had. And then we thought, oh, maybe there is something. So what we did is that we've built the, we used Kolmogorov-Smirnov method to build this kind of correlation sort of matrix. And the lighter the point is, the more there is the, not chance, but reality that these dimensions do not correlate with each other. By correlation, I mean like how close they are, basically, right, as values. And the darker the point is, the more correlating they are. And then we transform this into variance inflation factor. And we realized that there are patterns. Even here we see patterns, but here we see, okay, some dimensions are always correlating with each other, and we called them friends or buddies. So we decided to group them in one chunk in that split vector. And then we ran the clustering, and after that we got like 12% recall increase by doing like nothing in the underlying engine, just shuffling the vector. This looks like black magic, I know, but it's just.
This method is before you cut off.
Yeah. So first layer is to kind of reshuffle them and then feed to the algorithm, and it will do its thing. And and in the end, we measure the recall, right? Because the way recall is measured is that you have a collection of ground truths, right? So ground truth for this vector, here are the answers that should be present. And then you compute the overlap. Cool. We are running out of time. Any more questions on vector search? I just wanted to show you a bit of, well, actually, maybe I stay here. Yeah, I guess it won't be too much new for you, but especially those who know what RAG is. So if I just run, like, so I have a question like this, signal boosting. Does someone know what signal boosting is? No, it's like in telecom, it's related to how signal is increased in like amplified. But in search, it means completely different thing. It's like, so when users use your product and they click on products, you can collect those clicks and then you can boost the products based on that information next time. Right? So it's basically like, it's a signal which is invariant of the query. So you just store these clicks and you keep accumulating them. In other words, it's popular items that will pop up to the top. And so if you just run a basic vector search, it gives you, here I've indexed a book on search, and it gives you like portion of a section where I think it discusses the signal boosting. And if I ask a vanilla LLM, Gemma in this case, it talks about telecom and wireless communication systems. So it has no idea that what I'm asking is related to search, and there is no way for me to tell it. Well, maybe I could inject something in my query, but then if I do RAG on it, meaning that I will ground the answer using the sections that you have seen before, then it will actually tell me that it's just a technique that aggregates and boosts signals, so click events, and then it uses that for relevancy computation. Not the most obvious answer example, but it's just one of them. So we have like 10 minutes or so. Any questions so far? Yeah.
Chunk is only 50 tokens versus the whole document very long. When they get run through the embedding, what's the nuance being represented?
Oh, you mean like if the chunk is too small? Is that what you're asking? Or
I imagine they're not always
like long.
Maybe
Yeah. Yes. Yeah, exactly. So, well, the way we will do it in the most basic form is that we know the input capacity of the model, right? So the encoder can encode, let's say, 384 tokens, and that's that. If you provide more than that, it will chop the end off, and you lose that information, and it will just retain what it can feed. But if you provide less than that, it will use padding. So it will add zeros or some symbols. Yeah.
Well, fewer than 400 dimensions. Now the opening has like 3,000.
Yes.
What is the optimal sort of length of number of tokens you can?
I think. Yeah, I think the answer lies more in the direction of what is the structure of the document, rather than in the space of what the model can do. Although it's better to pick the model that has more capacity. But again, it's not just the capacity thing, it's also what the model was trained on, right? For example, was it trained on the topics that you care about? And if it wasn't, you probably need to choose another model or do some fine tuning of that model. But yeah, if you, and I'm not sure if I will show that, probably yes. But the idea is that sometimes in the book, the section starts in the end. So you just have the heading, but the text continues on the next page. And the way, well, we will implement it here is that we will split document page-wise, and then we will chunk those pages. So we will never cross the page boundary. And this is where I can challenge like this implementation and say, hey, why not actually not chunk by pages? And then what? Then how do you find the boundaries for the chunks? Maybe it's headings, maybe it's something else. And there are different methods that you can use. And one of them I ask you to do in the lab. But let's just really quickly, you see these, right? Will this work? Hopefully, if demo gods are merciful, I'll show you the demo. Basically, what it does is that it initializes models, like it loads the encoder model, which is the sentence BERT model, and then it loads the gamma model. Everything is local, so it doesn't do any API calls. So I could unplug my computer from Wi-Fi now, and it will still work. And okay, let's choose some question like, can you give me a summary of the RAG paper? And let's choose the RAG paper. So first, you guys see that, or should I zoom in? Yep. So first, it just reads the PDF. It extracts sentences using like one of the libraries. It then chunks it up page by page. And then it computes embeddings. And here it prints like, actually it found only 77 things to compute embeddings on chunks, because the paper is not very long. And so it's quite quick on a CPU, so I don't even need a GPU. And so for the results, well, it's still generating, but for these are like the responses from the vector search part, and you can see the score. I think I used the cosine similarity, and it's like 0.7, not that bad. It also gives me the page number. So coming back to the idea of providing references, now I can actually provide a reference. Let's see. Oh yeah, so here, what it did is that even though I did the vector search, I did it in vain because it didn't use that information. It just asked the vanilla LLM what it thinks about RAG paper. And you could say that by reading this answer, it's fairly okay, but it also doesn't go into too much detail. So it doesn't discuss, oh, there is even like some chopping here. I don't know what happened. But then we can say, okay, let's do RAG. So when I switch to RAG, it also takes some time to run it. Vector search runs really, really fast, but the generation takes maybe like 20, 30 seconds because I'm running this on my laptop. So if I was running this on like GPU machine, it would be instantaneous almost. But yeah, here it takes time.
First part have the same result.
Yeah, the first part we have exactly the same results. I mean, this vector search just runs it against the chunks. But in vanilla case, we do not use these chunks. And I mean, of course, I would optimize this a bit not to do it. In the RAG case, we will use these chunks. And we will just create a prompt with that. It takes. Huh?
Somehow the appendices is
the first result, yes.
You
Yes.
don't expect the summary or the conclusion to be that.
Yeah, I think it is. I don't know, it takes a bit more time than I thought, but I think I have this here in the README. So yeah, it does sort of decompose the model. So it says like, hey, we are talking about Actually, I think this is not a complete answer. Hold on. Yeah, this one. Yeah. So says achieve state of the art. It's a novel approach. Actually, it does miss something here. This is very interesting. When I generated this at home, and that interestingly goes back to what LLMs can like sometimes randomly do. It actually mentioned BART model here, but now it doesn't. I don't know what changed. That would be interesting to check. But in any case, the previous answer was much more grounded. And this is what you see here. So it mentions the parametric BART model. Here it doesn't generate that anymore. That's very interesting and confusing as well. Yeah, the chunks, the top 5, I think, or top 10. Yeah. Which can also create noise, but yeah. And then the same code is in the form of notebook, which is provided on GitHub week 5. So what I would like you to do before Thursday is to go through this notebook and set it up so that it runs on your laptop. I hope everyone has laptops. But if you run into any issues, we can try to solve them on Thursday. For example, if it's too heavy for you to run the LLM on the laptop, we can maybe change that to an API call to Gemini, or you can also run it in Colab. So if you have the account, you can also use GPU and run it there. It's much faster. Question? Yeah. Go ahead.
So I think about why it's a different one.
Yeah.
Now.
Yeah.
That actually, like, isn't that expected in a way that we're talking about a probabilistic system, no, which is not.
Yeah, I think I know why it gave a different answer, because I copied it with the bullet point.
Yeah,
So it's funny how sensitive LLMs are in general, right? So yeah, I think, yeah, we will see probably the right answer here. But let's wait until it does that. But while we do that, there are, yeah?
Can the LLM still, even if it would get the exact same results, it would still generate a bit different answer, like leave out.
It could, I think. But I think the power of RAG is that it kind of like makes the model zoom in on the data that you gave, because, and that depends on the prompt, right? Because the way the prompt is written, and you will see it in the code, is that it says, hey, don't overthink, don't give me the reasoning process, just look at these examples and summarize them in the most natural way. And then it gives examples of how to do that. So in other words, it says, do not look elsewhere in your learned representations, just look at this. And
doing in the prompt way the templates.
yeah. Yeah. Yeah, but yeah, so you kind of like ground the LLM. Lab. So for the lab, I have two kind of like groups of tasks. One is basic, and I don't want to like demote the importance of it, because I think actually when I was preparing myself, I spent multiple weeks thinking about these things and they didn't work, and like, so basics is good. Basics is not the worst, the bad thing. Like think about how would you solve these basic things as well. But if you feel like you are advanced user of RAG, do not pick basics unless you think that they will bring any value. And if you're familiarizing with RAG, please pick the basic tasks. And so for the basic tasks, I have two tasks here. One is that you just use the same code that we have on your document. So maybe you can pick a course paper or something long enough, let's say. And also, ideally, you try a different language than English. It would be very interesting where things break, where they will work, what thoughts will arise from that, right? And also, like, how does it influence on like chunking? Because in the notebook, you will see, I didn't have time to show it today, but first you run statistics on your data, and then you choose the chunk size based on what you see on the screen, right? So
there's some limitation now on the size.
Yeah.
Like 500.
Yes. Oh, no, the size of document, no. I mean, if it's not a 1,000,000-page document, it's fine. It's okay. The book I have, it has 528 pages, and it's fine. It's fine. It will be like 1,000 dimension, 1,000 vectors. It's not that much. And then, so of course, think about assessing quality and so on and so forth. And the other task, I think it's a little bit more advanced, but not that advanced. If you, and I do provide links where to look at it, even in the code shape. Just implement another chunking algorithm. So do not implement, so look at the implementation that we did there, which is fairly basic. It just chops, text in chunks. Use semantic chunking. So semantic chunking will, it's more computationally heavy. It computes the distances between subsequent sentences in your text. And as long as they are close in distance, it keeps it as part of the chunk. The moment they're too far apart, it will split. It will put a line and say, okay, new chunk begins here. Makes sense, right? And there are other methods, but semantic chunking is one of them. And then with asterisks, like I was thinking, if you haven't done agentic RAG or graph RAG, maybe it's a good time to look at that. I think there is a bunch of code available, and like you can try it out if you haven't tried. For agentic RAG, you can come up with your own task. Here, I just give an example. For example, you could detect the intent that the user wants the stock price, and then go and look to some API, and then retrieve the stock price and return as the answer. Or you can come up with some other, like your own idea. And then graph RAG is based on knowledge graphs. So it's a different representation of your data than dense index or like vector index. There is code. There is even code on top of that code, which makes it easier and so on and so forth. We can look into that later, but you can also do some maybe research ahead of Thursday. There are a bunch of links here in the slides you can take a look at. Couple of books. This book I am indexing in the RAG application and searching through it, but it's basically a very interesting book which focuses on using LLMs to empower search, like traditional information retrieval. And then there's another book which is fairly recent, Prompt Engineering, which covers a lot of techniques how you can implement better prompts, because the final quality of your application depends on prompting quite a bit. I think that's it. Sorry for taking over time. No, we are just 1 minute over time. Good timing. Any questions on lab or?
One question, I think we touched it already a bit, but like about chunking, if you think about RAG, and for example, like you have books or articles and they have like chapters and sub-chapters and things like that. So,
yeah.
So are they like any sort of extensions that, okay, we give more weight to title or something like that?
No, at least here, it's very basic implementation. What it does is that it looks at the length of the sentence, and if it's below some threshold, like 30, and usually these chapter titles are, it will drop them. It does sound counterintuitive, because maybe the user is looking for something that correlates with the title, and you can dispute that. You can like remove that filter, index everything, and then see what comes up. But the problem is that if you don't have like some kind of link between chunks, right? So saying, hey, this is the title and I'm computing and the embedding on it, and this is a separate chunk, which is the text behind that title, then I don't think there is value. But maybe you can come up with some approach, or at least experiment. How would you do it? For example, just combine title and text. Will it give you better response? Yeah. Let's see, did it compute?
Do you have any things where to get those different jump methods?
Yes, I do. There is this tutorial, which is like a notebook, and it goes into different levels of splitting your document. And you even have semantic splitting there. So it's not exhaustive. There are other methods. And I also link a paper on that.
Did you say that was an old book?
Huh?
Did you say that's an old book?
Which one?
The one you just showed with the different with 5 levels of text splitting.
Ah, it could be. I don't know. I didn't say that. I don't know.
Okay,
No, I don't know. So there is a paper from a company called Vectara. So the founders of this came from Google, working on BERT distillation. So they actually discuss semantics chunking, but they also list the methods. So you can take a look at this paper. At least you will know that they exist, and then you go and find the implementation, or maybe they're like easy enough to implement in code, you know, at least experiment, right? Because all you do is that you have an array of sentences. Now, how do you combine this arrays into chunks? That's the idea.
As you give back the full text and ask it to chunk it, maybe fine.
Oh yeah, you can do that too. Yes, that's a clever idea. Yeah. Why not? Huh?
This is a topic
yes.
I'm quite interesting. You know, the philosopher Wittgenstein wrote a book commonly called Tractatus. He writes in a very specific way, where it's like 1 to 7, like 1.1, 1.2. Each one is one statement. There's already chunk for you.
Yeah.
I wonder how you can do that with other text.
There is another method that well, maybe we can discuss it next week. So the method is what you described. Instead of thinking that, oh, I have a document, I need to chunk it up, I have basically the content page, all the titles and subtitles, and then it acts as an agent reading this page as if you would do it. So it would read like title after title and then reason about it and think, okay, is this the title that I should stop and kind of jump to the text or something like that, right? So it's more like towards agentic nature, and it's much more interesting, I think, and probably it resembles how we do things, rather than here we kind of do artificial splitting of text into chunks and then hope for the best, right? Which is not probably ideal.
It's vectorizing any difference, or this was all about the text?
This is just only text, but in next week I will discuss multimodal LLMs and give you some examples. Yes, and also RAG on top of them. Yep. Thank you. This was cool. Really intense. Lots of ideas. Yeah, and if you have any questions, just shoot them in the chat or email before Thursday. But on Thursday, we will continue practicing. Thank you.